Let's do a review. In the previous chapters, we discovered that the universe is not homogeneous, that homogeneity was never really an option. You only have quote-unquote statistical or large-scale homogeneity, which is in reality a 1/r relationship, which produces a gravitational redshift that is aligned with Hubble's law. So that we don't have a cosmological redshift anymore. We have a gravitational redshift due to the structure of the universe. This perspective is observer-focused, you can call it, observer-dependent. Our metric is centered around the observer or the emitter, but we're building it around the observer. We're constructing it backwards from Hubble's law, from our perspective. And when we do this, we end up with a horizon of around the same distance as the Hubble horizon, the Hubble limit, which is around 13 billion light years, or 1.28 times 10 to the positive 26 meters. So when you're looking at a star that is that distance from you, it looks as though the star is a black hole. It's a coordinate artifact from the choice of coordinates. Now in chapter 4, I give a brief historical overview of both the cosmic microwave background radiation and Hawking radiation. And at our horizon, we have the emission of Hawking radiation. Now it's very low temperature. It's like 1.4 times 10 to the negative 30 Kelvin. But this radiation is not emitted by a star. It comes from the horizon condition itself, from the geometry itself. And it feeds back to us, and it travels that entire distance, that 1.28 times 10 to the positive 26 meters or just meters. And from that distance, it has to travel all that distance through that geometry, and so it's blue shifted as it approaches you. Now my prediction for this was that it would be 1 Planck length from the horizon, and I tried for a long time to make it 1 Planck length. It almost broke me. I wanted it to be 1 Planck length. It's 2. It's 2 Planck lengths. 2.15, but we're doing a little bit of rounding with the Hubble constant. So there's a little bit of play within the Hubble constant. And so it's probably exactly 2 Planck lengths. That's the way I would fine tune the universe, is we use the emitted location. Now that emitted location is very sensitive. At some distance near the horizon is the way that mainstream physics describes the location of Hawking radiation being emitted. Some distance near the horizon. When the Hubble constant is 72 kilometers per second per megaparsec, it's that 2.15 Planck lengths from the horizon. That's where you get the right temperature to be able to observe it from the same distance, and it would equal what we observe today in the cosmic microwave background, that 2.725 Kelvin. So not only is this actually a remarkable find, prediction, discovery, whatever, the fact that, and what I mean by that is that it's the observed temperature of the CMB can be aligned with the cosmological redshift, the empirical values of the cosmological redshift, and the horizon, and the Planck length. No adjustable parameters. So, in other words, if you change the value of the Hubble constant, then everything else shifts. And so, you have a very, very, very little fine-tuning to do. There's a very small range of play there. And it's all like observational data would fine-tune that to the exact values. Now, not only is that remarkable, like that is extremely remarkable. That is way better of a prediction or a model than whatever inflation nonsense and relic radiation that the Big Bang Theory describes the CMB as. But, in addition to that, we have several anomalies in the CMB structure that are present in Lambda CDM that doesn't know how to explain these. It's stuff like the hemispherical power asymmetry, the low quadrupole, the cold spot. These anomalies can be resolved naturally when you have this structure of the universe impacting these observations. It's not, we don't have to fine tune our theories about the origin of the universe and whatnot. It's just the structure and the observer's relationship to that structure that creates those stuff like the cold spot.